Hi everyone. So whenever current flows between 2 points, it does so because there's a voltage difference between those points. So if I have point A here, point B here, current's going to flow due to that electromotive force there. The power that's associated with that flow is given by this formula here. Power is current times the voltage difference there. And that really follows from the definition of power, the definition of current, and the fact that the potential energy associated with voltage is just Q times the voltage difference between them. Mix those three formulas together and this is the formula you get. As a consequence, this formula for power is always true regardless of how the current's varying or the voltage varies or whatever. It's always true that the total power being consumed at a particular moment in time is the current at that spot in space and the voltage at that spot in space. Now, whenever current's flowing because of a potential, that flow is happening, at a fundamental level because of Newton's second law. There's a potential which implies that there is some sort of electric force present. That force accelerates the charge, pushes them, moves them, and therefore you might expect that electric charge accelerates under the influence of a voltage source. And that is true. An example is, the old CRT cathode ray tubes, which we used to use in our TVs, and basically you have a hot piece of metal which would boil electrons off, and you have a strong voltage source, and it would basically pull those electrons to the screen, and those electrons would slam into the phosphor on the screen, causing a little burst of light. And that's how the old TVs used to work. Now, this acceleration of electric charge does not typically occur in electric circuitry for two fundamental reasons. The first reason is maybe simpler to understand if you imagine a water hose. And imagine that water hose is filled with water. I walk over, turn on the spigot, instantly water comes out the other end. Why? Because that's the water that's ready to come out. It's not the same water that's coming out of the spigot, right? Basically, that water pushes the rest of the water, and that influence propagates at the speed of sound, actually, through that water. There's some viscous effects there, so it's a little bit less, but, effectively, the speed of sound, that influence is propagated, and you've got water pouring out of the hose. Well, the same thing happens in an electric circuit, that the wires are full of electrons. And so if I turn on a voltage source, the electric influence of those electrons propagates through at the speed of light in this case. The actual speed that the electron flows through the wire is typically quite small, something on the order of 100 to 300 miles per hour, which compared to the speed of light is quite small. So so when you flip on a light circuit, you expect the light to show up instantaneously, effectively the speed of light. The second main reason is, perhaps more fundamental, and that has to do with the fact that in every electric circuit, in all types of electric flow, there's a certain amount of drag associated with that flow, an electrical viscosity, if you will. And we call that resistance in this context, right? And so this drag actually, if you imagine a parachute, parachute drops through, it hits terminal velocity. So instead of accelerating, it actually moves through the flow, it moves through the air at a constant speed. And that's because of the presence of a certain level of drag. Well, the same thing is happening in an electric circuit. So basically, the electrons accelerate up to a speed at which they hit their terminal velocity in the electric circuit, and then they move at that constant speed. And that constant speed is why the current everywhere in the circuit is the same value. If the electrons were actually accelerating, the current would be different at different values because you'd have more charge flowing per second. But you don't. You have the same amount of charge flowing everywhere, in a conductive wire, because the speed of the electrons are at their terminal velocity. Now, a resistor, a perfect and ideal resistor, has this kind of a relationship between voltage and current. perfect straight line. That straight line is really the definition of resistance. And this equation here is called Ohm's law, and basically is the relationship between voltage and current, and the resistance is effectively the slope of this line. That resistance is, Ohm's law is true only by definition. So if we have a circuit in which the resistance or the drag is not linear, Ohm's law won't work. But for us, we are going to begin by using simple resistors, and for simple resistors, Ohm's law will be valid, and that's what we will be using. The SI unit for resistance is the ohm.